Welcome to Chemistry 100. We're going to look at Chapter 10, Acids and Bases. We're going to start with a quick demo showing an acid-base indicator, which is red cabbage. Okay. So for this chapter, we're going to start by doing a acid-base indicator test. Where I'm going to show you the acidity that is in our normal breath. So I've taken red cabbage and torn it into fine shards, and I'm going to boil this for 2 minutes to extract the dye that is in red cabbage. I'll see you again after this has begun to boil. Now that I've given it plenty of time to boil and extract the dye, I'm going to set it aside to cool. Now that I've allowed it to cool, I'm going to try to decant the fluid. Purple dye, that's the anthocyanin. Essentially the dye that gives it its purple color. And this is an acid-base indicator. That depending on its environment, this dye will change color. Don't really need to worry too much about the structure, other than that essentially we undergo molecular rearrangements through the addition or subtraction of a hydrogen atom causes the molecule to completely rearrange itself, thus causing a different absorption of light. To this solution of cabbage indicator, I'm going to add ammonia solution so that it turns from its neutral state to basic. Now, it will appear green to my eye, but it will appear, at least under the camera's view, as more of a blue. I'm going to get this, so mix it, so you can always see the colors changing. Stir this. This has completely changed color. That's more than enough. Now I'm going to attempt to blow CO2, blow air into it, so as to change it back. As you see, it has gone back to its original purple color. That is because CO2 in your breath is mildly acidic. As it binds to the water molecules, it will become carbonic acid, which is, well, an acid, as we'll see a little bit later. And it replaces the hydrogens that were lost when I've added ammonia. If I continue to add acid, it will change further, as we'll see when I add this vinegar solution. So I add this vinegar solution. As it turns even brighter shade. It's actually more of a pink red. So we can use the we can use the cabbage as a natural indicator of whether something is acidic or basic. The colors will tell us approximately how much acid or base is present. As we saw in the demo, the active ingredient was anthocyanin. While you don't need to worry about the actual structure of it, note it was made up largely of aromatic family of hydrocarbons, and that with some alcohols and oxygens that could both absorb hydrogen or lose hydrogen to rearrange and switch around double bonds, which of course double bonds absorb different wavelengths of light. So more double bonds or less double bonds would change what light it absorbs, thus what color it will appear. And so depending on whether this was an acid or base, we could see various color changes. This was an example of one of the simplest and well-known acid-base indicators, but was even simpler one would be regard the litmus test. Now, an acid-base indicator is just simply a dye that will change, lose, or acquire color as the solution containing the dye changes in acidity or basicity. Now, the litmus test was essentially a pink mixture of a substance developed from a plant in the Netherlands. The dye was, erythrolitmin, which was red in acid and blue in base. So the litmus test, they would impregnate paper with this erythrolitmin and then test it against acid or base. Now they would specifically pre-treat the paper with various colors so to make ease of visibility. So they made some blue litmus paper and red litmus paper, which essentially they used red paper and impregnated with the litmus, and blue paper and impregnated with the litmus. And so when they dipped the red one in acid, it stayed red. But when they dipped the red one in base, it would turn blue. And then you could easily notice, oh, it's blue, as opposed to the undipped part, which was red. And the blue one would obviously stay blue in base and turn red in acid. And so, oh, this is clearly acid. But this was originally only used for just acid and base indicator. But now the term litmus is in the colloquial language. Like we use the litmus test for politicians, but that was originally only for acid and base. Now acids will taste sour. They will turn litmus red, and they typically will react with metals to produce hydrogen gas. And when we say it tastes sour, your tongue is actually measuring electricity produced by protons, hydrogen cations that are recognized by the tongue. So if you licked a battery, which I wouldn't suggest you doing, but if you did, you would taste sour. Acid comes the Latin acidus, which means sour or sharp taste. Now bases, they tend to be bitter. They'll turn litmus blue, and when you feel them, they would feel slippery. Now, I'd suggest you do not try to actively taste your chemicals or mix random chemicals in the home. There's a reason why many of the scientists, despite being upper crust people, didn't have the longest life expectancy. I mean, I want to say like, oh, the peasants lived very long. No, they died pretty quickly. But when you can afford good living conditions, you'd expect yourself to live a little bit longer. But yet these people tended to die semi-relatively youngly, whether it's due to they breathed in too much chemical that's torn up their lungs, or like we learned about Francis Bacon, died of pneumonia doing a chemical experiment, or during an experiment where it trying to refrigerate meat. Some of these things are a little bit less safe than you believe. Now, most acid-base reactions are an example of neutralization reactions, which is a reaction where acid and base will react to produce a salt. And a salt, well, we've seen salts before. A salt, in this case, is defined as an ionic compound, other than water, that is produced by reaction of acid and base. There are many different examples. We can have hydrochloric acid mixed with sodium hydroxide, and it produces sodium chloride salt. Just basically table salt and water. We can mix hydroiodic acid and potassium hydroxide and produces potassium iodide, which is one of the key components in iodized salt. and water. If you mix sulfuric acid and magnesium hydroxide, you form magnesium sulfate and 2 water molecules, which is the key component in Epsom salts. And carbonic acid mixed with calcium hydroxide forms calcium carbonate, one of the key components of, I think, chalk, if I'm not mistaken, water. Now, all this is well and good to say this is an acid-base reaction, but what are acids on a molecular level? We need to look at that. Now, there's no one single answer that will give us this. It all started in 1778 when Antoine Lavoisier tried to define acids. I mean, acids were well known well before that. Acids were known in early Greco-philosopher time, but we didn't have a good handle on what made up an acid. Well, Antoine Lavoisier proposed that all acids must be formed by the combination of oxygen and some other element. While this is wrong, he's not that far off. At the time, all known acids were oxyacids, and that comes from the original naming of oxygen, discovered, well, at least helped name by Lavoisier, where oxygene means sharp forming, or essentially acid forming, meaning that sulfuric acid is a combination of hydrogen, sulfur, and oxygen. Carbonic acid is hydrogen, carbon, and oxygen. Phosphoric acid, hydrogen, phosphorus, and oxygen. Boric acid is hydrogen, boron, and oxygen. So nitric acid is hydrogen, nitrogen, and oxygen. But the thing of it is, there's plenty of oxygens that weren't discovered at the time. This was true up until the American Revolution, but all the acids known at that time contained oxygen. Lavoisier eventually would meet his fate at the guillotine, as we mentioned earlier. Now, as I said, there's plenty of other acids not under that situation. While this was known as a salt acid, capturing the marine acid air, which was hydrochloric acid as a gas, wasn't discovered until Gay-Lussac, who we'll talk about a little bit later in the gas chapter. But it was discovered by Gay-Lussac in 1887. It was named eventually muriatic acid, which means pertaining to brine or salt. By discovering HCl as a non-oxygen containing acid, this would help shift the role of acids not to the oxygen in them, but the hydrogen. In 1887, savant Auguste Arrhenius proposed that acids must produce a proton, that all acids should produce a proton when dissolved in water, and all bases would then have to produce a hydroxide. And now, while this definition is valid, this definition does not cover all possible acids. We're going to go through a couple different definitions of acids, all of which are valid, but some are more general, which covers a wider range of acids. It's kind of one of those square and rectangle thing, that all squares are rectangles, but not all rectangles are squares, because a square has to have 4 sides of equal length and 4 corners of 90 degrees. All rectangles just have to have 4 corners of 90 degrees. Oh, this definition by Arrhenius is good, but what happens, but this takes place in the absence of water and is far too limited of a definition. So in 1923, a Dane by the name of Johannes Bronsted, an Englishman by the name of Thomas M. Lowry, not Lowry salt, different Lowry, but would independently define what it means to be an acid and a base. And we're going to use their definition for the majority of this chapter. The Bronstedlowry definition for acid is any substance that can transfer a proton to another substance. That is pretty much the same as the Arrhenius definition, produces a proton. However, the base is now defined in regard to that proton, and that a base is any substance that can accept a proton. It no longer has to produce OH, it just has to accept a proton when I add an H. That in the case of an anion like F minus could accept a proton to form HF. A molecule like HCl can mix with NH3 to form NH4Cl. A salt, ammonium chloride, without the presence of hydroxide or without even a solvent present. We could mix them in gas form and they will combine together. Now that we've intrinsically linked acids and bases, there's one other we should discuss. In the 1920s and 30s, Gilbert and Lewis would further change the definition again to say that an acid was a electron acceptor and a base was electron donor, meaning that we no longer need even a hydrogen present. However, hydrogens, because they are H plus, they are lacking electrons. And so when they form onto something, they are indeed accepting electrons. And bases like hydroxide have a bunch of lone pairs, which they will then donate to make make this a base. Now I'm going to show you a couple examples of this in just a few. Okay, so Arrhenius acid, something simple would be let's say NO3. That because Arrhenius, it just has to split into H plus and NO3 minus. Well, a base would be something like KOH, that as it splits apart, it forms K plus and OH minus. That's all it takes to be an acid and a base, Arrhenius. But that doesn't cover all possibilities. Now, let's look at the combination Bronstedlowry. So we also have an acid and a base together. So in the presence, if I mix nitric acid and KOH, remember that was our base, that was our acid. Now, what has happened? We form HOH and KNO3. That if this was part of our acid, it has given away its proton. It's given away its proton. If we looked at the anion as being the base, it has accepted the proton to form the HOH. And the beauty of this is that now we don't have to have a hydroxide. If I just wanted to put F minus, this is still our acid. But now we have this being a base. That as we draw the arrow, we have HF, which is gone from acid. The base has accepted. The base has accepted the proton. And now the acid has donated the proton. Because of the nature of this, if this were to go backwards, this would be an acid donating the proton back to here, back to the base. That we don't have to have hydroxide. I can mix in, say, HCl and NH3. NH3 is our base, HCl is our acid. You'd have NH4 plus, which is now an acid, and Cl minus, which is our base. Now, all that's well and good for Bronstedlowry. Now, the advantage of things like of the Lewis acid is that we don't even need hydronium. We'll look at our hydroxide. If I mix just H plus and OH minus, in terms of a Lewis acid, if I put the electrons around this, what's happening in the Lewis acid is the base is the electron donor and the acid is the electron acceptor. So the electrons are going over to form that H-OH bond. But now we could do something like this. BH3 and NH3. NH3 was a base up here. It's still a base right here. But BH3 does not produce a proton. It isn't, but yet it is an acid. BH3 would have 6 electrons, too short of having the octet. It has no lone pairs. So what would happen is the electrons on ammonia would donate into the boron to form BH3, NH3, a molecule right here, an adduct, if you will, that everything has an octet now. And this is what Lewis acids would allow us to do. However, we're not going to focus on Lewis acids because hydronium is our key component we're going to look at in this chapter. Now, a lot of what we're going to deal with is going to be water. Water is our universal solvent. That's where we live. We live in water. We die in water. Water will have the most unusual acid-based properties of pretty much all the molecules because it is both an acid and a base in equal measure and at the same time. Water will naturally split apart into H plus and OH minus. Now, H plus and OH minus are not the best way to look at this. We're actually going to look at this as hydronium ion rather than H plus. What we should be looking at is at H3O plus. Hydronium is ion that forms when a proton is bonded to a water molecule. That's a little bit more stable way of looking at this. But this splitting apart of water is because water is what we call amphoteric, Greek for amphoteros, meaning either of two, that it splits apart both into acid and base at the same time. Now, this is an equilibrium dynamic process. So it's going to be constantly shifting and trying to get to a point where the reaction is going the same speed forward as the same speed back. And we're going to have a certain quantity of hydronium and hydroxide as well as water in there. List ionizations and recombinations always going on at the same time. That we don't drink water and then get burned by acid and base because it is constantly combining back together to form water. And the amount of hydronium and hydroxide at water at any given time is rather small. When a reaction is said to be at equilibrium, the forward and reverse are occurring at equal rates. And the concentrations of each product is fixed and measurable at a given temperature because of this equilibrium scenario. That in pure water, which is perfectly neutral, neither acid or base, the hydronium and hydroxide are equal at 10 to the negative 7th molar at 25 degrees, meaning that there's 10 to the negative 7th molar hydronium and 10 to the negative 7th molar hydroxide. And that is a really small number, by the way. That's 0.0000001. Now, when we talk about strong acids and strong bases, a strong acid doesn't depend on its actual concentration. It depends on its degree of ionization. That when we talk about hydrochloric acid being a strong acid, it's a strong acid because it irreversibly splits into hydronium and chloride. And so when we look at the concentration of hydronium in solution, it is essentially equivalent to the amount of hydrochloric acid that it originally started with. So when we look at the concentration of acid, it is essentially the starting concentration of our HCl. Of course, we should add in the hydronium that was already present in the water, but usually that is so small as to be insignificant. Now, when we look at acetic acid, which is our active ingredient of vinegar, we call that a weak acid because this is a reversible reaction that while it can split into hydronium and acetate, it can also reverse back to reform the acetic acid in water again. And because of this, only part of it ionizes. And because of that, you don't get the full effect of hydronium. The concentration of hydronium is not equal to the starting concentration of acetic acid. And so if we had equal amounts of acetic acid and hydrochloric acid, it would have far more hydronium from the hydrochloric acid than the acetic. Hydrochloric acid ionizes completely, while acetic only partially ionizes and thus would be weak. And so the hydronium concentration of acetic acid will depend both on its starting concentration and its ionization potential. In this case, the extent of ionization would depend on the acid, and there's many different weak acids like this. And so each one has a different ionization potential, and so each one has a different strength. Hydrofluoric acid has an ionization potential. Carbonic acid has a certain ionization potential. Phosphoric, certain ionization potential. Each of these is going to change depending on what you have. Hydrocyanic acid, different ionization potential, so different strength of acid. Now, how do we actually measure this strength in acid? How do we measure the concentration of hydronium? Sure, we can measure out the direct concentration, but it's really kind of hard. How do we try to justify? If I say the difference between 0.01, which is 10 to the negative second molar, versus 0.0001, which is 10 to the negative fourth molar, these are kind of big changes, and it's kind of easy to miss a decimal here and screw things up. So rather than deal with these scientific notation, which can still be rather complicated, Danish scientist by the name of SPL Sorensen in 1909 proposed to treat them exponentially. And so we invented the pH. The pH is a measure of a solution's acidity, where pH is a negative logarithm of the hydronium ion concentration. So take the negative base 10 log of this, and so it'll turn that into a simple number. So our neutral water, which is 10 to the negative 7th molar, when we take the log of 10 to the negative 7th, it gives you negative 7. By taking that negative, it becomes positive 7. So neutral water is 7. Whatever you want to call pH, pH being a power of hydrogen or power of hydronium, there's various reasons why pH is applicable. English word for could be power, with French for puissance, and German potence, which all three of these are the three dominant scientific languages at the time, which is kind of sucks for the Danes, but you know, a lot of people spoke more than one language. But that's so we have a power-based function of measuring our pH. Now, acids, by definition, will have a concentration of greater than 10 to the negative 7th molar, such as soda, which would be 10 to the negative 3rd molar. Bases will have a hydronium concentration of less than 10 to the negative 7th molar, such as milk of magnesia, which is 3.16 times 10 to the negative 11th molar. Due to the nature of the hydronium and hydroxide concentration from water, it's because it's amphoteric, we can actually measure the concentrations as a product of hydronium times hydroxide. The equilibrium expression for water, Kw, is constant, and that at neutral water, when 10 to the negative 7th and 10 to the negative 7th, you have 10 to the negative 14th. And so we can look at the pH scale running between 0 and 14, where 7 is smack dab in the middle, neutral, meaning that as acid increases, base will have to decrease. And as acid decreases, base will have to increase. So pH of an acid will always be less than 7. The pH of a base will always be greater than 7. And each pH unit, remember, is a 10-fold increase in concentration. So going from pH 7 to pH 6 is increasing the acidity by a factor of 10. Going to pH 5 would be increasing from neutral water by a factor of 100. So pH 1, far from being a mere change in 6, but it would be a change in 10 to the 6th. The change in, essentially, a change in what? A million. Soda in this case would be pH 3. Milk of if you drank milk, milk would be pH 6.5. So very mildly acidic. But when it spoils, we form a lot of lactic acid, which gives it that sour taste. So when it sours, obviously it's producing more acid, and so the pH would actually drop to lower than 6.5. If we were to look at and measure pH concentrations, all we'd have to do is simply take the negative log of our hydronium concentration. If I were to tell you the concentration of acid in soda is equal to, if hydronium acid concentration is equal to 1.8 times 10 to the negative 3 molar, how would you calculate the pH? You would literally just say the negative log base 10 of 1.8 times 10 to the negative third. Doing that, most logs are base 10 logs, by the way. So if I do that, I'll say negative log 1.8 times 10 raised to the power of negative 3. That our pH of that situation would be 2.7, say 4. 2.74. That's our pH. If I said the concentration of hydronium was 7.2 times 10 to the negative 9th, which would be in the basic region. The negative log of that, 2 times 10 to the negative 9th, negative log 7.2, 10 root negative 9 would be 8.14. 8.14. So that would be how you would calculate the concentration, the pH, measure the acidity. And all that's because we have that 10 to the negative 14th equals hydronium times hydroxide. So if hypothetically, if this was the concentration of hydronium, what would be the concentration of hydroxide in that situation? So 10 to the negative 14th equals 7.2 times 10 to the negative 9th times our OH minus concentration. To do that, you'll take 10 to the negative 14th divided by my 7.2 divided by my 10 root negative 9.
And that would give us OH minus equaling 1.3, we'll say 9 times 1, 2, 3, 4, 5, 6. 10 to the negative 6 molar. So you would have to agree the OH minus is greater than the H3O plus in this basic situation. Now, while we can measure pH with our litmus strips, we can also measure it with what's called a pH meter. pH meter is a voltmeter that has been calibrated to measure with electrodes that will measure the concentration of hydronium as a current produced. That we measure from a standard electrode how much current is produced as a function of hydronium concentration. And by measuring that and relating that to a scale, we're able to put this on the pH scale. Now, there's a wide variety of pHs in our everyday life that we can see, like gastric juices. So our stomach acids ranges anywhere between pH 1 and pH 3. Really sour lemons, 2.2 to 2.4. Vinegar can be between 2.4 to 3.4. Soft drinks, 2.5 to 3.5. Sour pickles, 3 to 3.4. Wine, 3 to 3.8. Oranges, a little bit less sour, 3 to 4. Tomatoes, slightly sour, 4 to 4.4. Urine, I wouldn't suggest you drink it, but can range between 4.8 and 7.5. Carbonated water or even rainwater will be 5.6. Cow's milk, 6.3. Human saliva, 6.4 to 6.9. Drinking water can be anywhere from slightly acidic to slightly basic. When eating, I guess our saliva goes up in pH. Blood is slightly basic. Eggs, also slightly basic. Seawater, getting a little bit more basic, 7.8 to 8.3. Sodium bicarbonate, saturated solution is 8.4. Calcium carbonate, 9.4. Milk and magnesia, 10.5. And household ammonia between 10.5 and 11.9. Now, some enzymes in the body are very pH specific, and they will actually stop functioning at too high of pH or too low of pH. That essentially the protein has folded in a specific way because of the acidic environment. And if you change this pH, it will unfold and thus be useless. The enzyme won't really work. Now, acids and bases are most common in food. The most common form we'll see is a carboxylic acid, which is a functional group of the C double bond O with a OH. We saw this in the organic chapter. It's the combination of the ketone or aldehydic functional group with a hydroxyl of alcohol. Now, the smallest carboxylic acid is formic acid. Formic acid that is present in the sting of red ant bites, which kind of tells us the name. Formic is from the Latin formica, which means ant. If you wanted to name it like IUPAC, you'd probably call it methanoic acid. Next one, acetic acid, which is vinegar, which should be ethanoic acid right beside it. We could keep building propionic acid and butyric acid, building to 3-carbon and 4-carbon acids. We have, citric acid down here. We have oxalic acid. We have this is carbonic acid. We have, what's this one? I'd like to say lactic acid and benzoic acid down here. All these acids we will see on occasion. Now, oxalic acid, for example, right here is a toxic compound that is in most plants, but in most plants, the concentration is too low to be of hazard. So, like, it's present in spinach and in rhubarb. But to eat enough spinach to kill you, you would have to eat something like 4 kilograms or something like 9 pounds of spinach to get enough oxalic acid to kill. Now, rhubarb it's not really present in the stalks, so it's safe, but it is higher concentration in the leaves. So if you eat the leaves of rhubarb, you could get sick and die. That's because of the oxalic acid. Now, propionic acid over here is the flavor in Swiss cheese. That if you've ever had Swiss cheese, it's kind of sharp tasting. It's because of this acid in there. Butyric acid, we talked about this. There's a rancid butter coming from butyrum, which was butter, Latin for butter. But often sodium propionate or calcium propionate is added to cheeses and bread and other baked goods as a method to retard the growth of mold and to help preserve the freshness. So if you take this hydrogen off and replace it with a sodium, it can be used to help stop mold. Let's see, benzoic acid down there. You often see this in the form of sodium benzoate, another preservative, especially in canned goods. Lactic acid down here is the acid in sour milk, which comes from the bacterial fermentation of lactose. But lactic acid is also formed in the body, part of the metabolism. That glucose in muscles become decomposed to form CO2 and water. However, lactic acid will end up building up during heavy exercise. And this lactic acid is responsible for the aching and tired sensation you feel in your muscles when you've, like, say, run a marathon and haven't got enough breath because you don't have enough oxygen to fully combust this down to CO2. Of course, and industrially, while it's not, I haven't shown on here, we also have sulfuric acid, H2SO4, which is produced somewhere in the realm of 44 million tons a year, because it's used either as a reactant in other experiments or a catalyst. We also form calcium oxide, which is known as lime, and something like 22 million tons used in the production of cement. But all these are organic acids that we'll see. Now, acid indigestion and heartburn, what actually causes that? Acid indigestion is brought about when enzymes in the stomach would digest your stomach just as easily as a flank steak, if not for the alkaline mucus lining on your stomach. The acid doesn't really distinguish. It dissolves through whatever it has. Now, as long as you have a good stomach lining, it prevents that from happening. But when that lining fails due to stress or some damage, the acid and the pepsin in your stomach will start to eat a hole in your stomach itself, and this creates an ulcer. And of course, like, you can get heartburn. Some of the heartburn is acid buildup can reach into your esophagus, which doesn't have that protective lining and can also burn there. So what antacids to do is they relieve the pain by neutralizing your stomach acid. The most simplest one would be baking soda or sodium bicarbonate, one of the oldest known antacids. That the goal is not complete neutralization. In fact, if you neutralize too much, you would cause a thing called acid rebound, which your stomach realizes, oh, I have no acid, and produces a ton more to replace what you've done. So you don't want to neutralize it all. You just want to raise the pH a bit, maybe a factor of 10 or 20, factor 10 or 100, so it doesn't attack your stomach lining as strongly. And if you completely neutralize your stomach acid, it would also shut down digestion. We just want to neutralize the excess. Like, so if you neutralized even 90% of the stomach acid, the pH would still be a 2.3. So it takes a lot to neutralize, to change the pH a lot. Changes pH with that much. So there's a lot of different antacids. The active ingredients could be aluminum hydroxide, calcium carbonate, magnesium hydroxide, sodium hydrogen carbonate with baking soda, potassium hydrogen carbonate. You could magnesium oxide. Magnesium oxide just works. It combines with water in your stomach to form magnesium hydroxide in situ. But all these could be used to neutralize stomach acid. Some of these are better than others in either how much acid they neutralize. Aluminum hydroxide neutralizes 3 acids per mole of aluminum hydroxide. Some of these are better because they don't contain sodium. If your doctor says, I don't want you to take too much sodium, you don't want to take sodium bicarbonate because that's going to raise your hypertension level. So you want something that has, say, magnesium or calcium. And so what happens? When you mix on like sodium bicarbonate in with acid, it forms sodium chloride and carbonic acid. Well, this carbonic acid can decompose back into water and CO2. And so you can kind of get that burpee sensation where you can have a lot of stomach gas after taking an antacid, where you could, anytime you have a carbonate, you're going to produce carbon dioxide. This is due to this is what creates the effervescent factor when you mix Alka-Seltzer with water. Such an Alka-Seltzer is 1 gram of sodium hydrogen carbonate, 0.3 grams of potassium hydrogen carbonate, and 0.8 grams of citric acid. That when you dissolve this in water, it starts to neutralize some of it and produces CO2. But as I said, people with hypertension should avoid sodium. People with bone degeneration should look for calcium carbonates. So try to add more calcium into the diet. Tums would be a better antacid in this case. Now, looking back at our Cabbage indicator, we saw that when I breathed in CO2, it became more acidic. And that's because what happened is the CO2 bound to the water and changed that to carbonic acid. Well, in the presence of ammonia, carbonic acid would form ammonium carbonate and be neutralizing out your ammonia. In the presence of excess ammonia, this is where it turns into the green color. Well, bluish green, really, when you have excess ammonia. When you have more carbonic acid, so you've neutralized all the ammonia, we get a mildly acidic solution, which was where we went back to our purple color. And when we added carbonic acid, we forced this all the way back to fully acidic. And it went into the pink color. See, carbonic acid can undergo various equilibrium depending on whether it going through the carbonate, hydrogen carbonate, and carbonic acid, depending on the presence or absence of acid-base situations. This is a thing that suffers from, and all equilibrium situations will suffer under the principle of Le Chatelier. Le Chatelier's principle simply states that when stress is placed on a system in equilibrium, the system tends to change in a way to relieve that stress. So if I add more hydronium or some source that donates hydronium, I'm going to absorb that hydronium away, neutralize that. If I add something that removes hydronium, I'm going to try to replace that hydronium and thus shift it one way or the other. In the case of carbonic acid, if I add more carbonic acid, it's going to produce more CO2 and water. If I add more CO2, it's going to produce more carbonic acid. More CO2 is going to dissolve. We have a K expression here that looks at CO2, water, and carbonic acid, that if one of these values goes up, the value on the other side must go up to match it, to relieve that stress. If one of these values goes down, the other must go down. That these guys will essentially be kept at equilibrium. That, as I replace one, change the other. And so this carbonic acid scenario is actually used to regulate the pH in the blood. If the pH gets too high, and so too basic, more CO2 will dissolve into the blood to make more carbonic acid to lower it back down. If it becomes too acidic, this carbonic acid will break apart into CO2 and we'll have less CO2 dissolved in the blood, thus raising the pH back up, thus keeping the pH of blood perfect to do what the blood do. Okay. So for this prompt, I want you to look up noted scientist Felix Hoffman. There's a little sign in the book, but you don't have to use the book. You can look up on Wikipedia, you can look up Britannica. You should note he has two major inventions. It's more like discoveries, but two major inventions. The first one, it's like, hey, yeah, that's really great. He invented, was it aspirin, I'd like to say. But there's something else he invented that wasn't quite as good. So I want you to talk and discuss in 150 words. 150 words how science and technology, even with the best of intentions, can go horribly, horribly wrong. Feel free to use other examples of scientific inventions that go wrong. Just make sure you cite your sources. Sometimes industry finds something new, they take it, they run with it, thinking this is the greatest thing since sliced bread, and then we find out later that, oh God, what have we done? What have we done? And sometimes science can be like that. Science and technology kind of get away from us. We find something new. If we don't always test it, well, at least don't always test it as good as we should, and then got ourselves in a pickle. So I want you to post a discussion on examples of science going wrong.